Hi guys. Hey, we are starting chapter 19. So this is one of the more important chapters as far as chemistry goes because it is all about naming compounds and balancing chemical equations. So basically it's kind of like the kind of learning the language of chemistry, and it's just a good chapter for getting all of those different points in. So we're going to stretch it out a little bit. We're going to do lots of practice stuff. It's partly the reason that I've been asking you guys to really make sure that you know your element names and symbols, because you're going to need to know them for this. So keep working on those. And again, here we go. Okay, so chemical formulas are the element symbol, and then also the and also also the subscript. And we've talked a little bit about that. I mean, just simple compounds that we've already talked about, like H2O, two H's, one O. And so you have symbols and numbers that are part of the formula. And you can have an empirical formula, which is what your book defines as, or talks about as, the relative proportion of atoms in a molecule. That basically means the most reduced form or numbers, and the molecular, which is the exact numbers. And so I've got glucose down here as an example. The molecular formula, we'll start with that one, even though I'm out of order a little bit, is C6H12O6, and so that's the exact number. If we reduce all of those numbers, 6, 12, and 6 are all divisible by 6, then you would have CH2O. And so it's a big difference. We typically will deal with smaller numbers, but it is important to know the molecular formula because those are exact. Okay, so now oxidation numbers. We haven't talked about these yet, but we've started dealing with them when we've talked about how the electrons are transferred or shared. And in the last chapter, when we did the ionic bonds, and we showed the transfer of electrons, and then we did like the +1 if it lost one electron, or the -1 if it gained one. Those are referred to sometimes as the charge or the oxidation numbers, and they tell how many electrons an element is likely to lose or gain or share. And they can be positive or negative, and they all go back to knowing the valence electrons. So still dealing with valence electrons. And when we're in class, we will do some more labeling on our periodic table, like the one on our wall that has the +1, +2. Those are oxidation numbers, and they will play a role in helping us write compounds, the chemical formulas correctly. Okay, so here are the rules for oxidation numbers. If you have a pure element, the oxidation number, and a lot of cases here on out in this PowerPoint, I'm going to put ON, capital O, capital N will be oxidation number, by the way. Okay, so if it's a single, a pure element, then the oxidation number is 0. And so it can be just a single element like sodium. It could just be Na, or it could be one of the diatomic elements that we've talked about, the Brinkelhoffs. Remember, you wrote those on your periodic table. If you see those, if you see an element by itself or one of our special diatomic elements, its oxidation number is 0. Okay. Number 2, the oxidation number of a monatomic ion is equal to the charge. So this is what we will label on the periodic table. And certain columns, as we see in the next one, certain families will regularly have the same oxidation number. And that is because of the number of valence electrons they have. It depends on if they have low electronegativity or high electronegativity, so if they're going to lose or gain electrons. And so this is what we'll label on our periodic table. Group 1 has an oxidation number of +1 because they lose one electron. Then group 2 has a +2. Group 13 has a +3 oxidation number. We kind of skip over those transition metals. Group 14 has a positive or -4, and that is because that's right in the middle of right, or about halfway to 8. Remember, 8 is kind of the magic number. So they are left with the decision to either just get rid of all of those valence electrons or try and gain to get 8. So that's why they have two options. Group 15, -3, because they typically gain 3 electrons. Group 16, -2, because they gain 2, and then 17, -1, because they gain 1. The sum of the oxidation numbers of the atoms in a compound must equal 0. So that's the +1, -1 equals 0 that we did when we were doing the ionic bonds. Transition metals are called transition metals because their oxidation number can change. Remember, transition means change. And so their oxidation number can change. It's not a drastic change, like it's either +1 or +2 or +2 or +3. They all are going to have positive oxidation numbers. And what the actual number is depends on the compound that they are a part of. And so typically for transition metals, you have to know first off what the other element, what its oxidation number is, and then you figure out the transition. We are not going to do a lot of those, but I want to make you aware why we're skipping that whole section when we're talking about this. Okay, so now writing formulas. Writing formulas, you have to know the oxidation numbers, and then you use those numbers to get everything to equal 0. Okay, and so the symbol contains you have kind of 3 steps. You write the symbols, you write the oxidation numbers, and then you balance or make the oxidation numbers equal 0. Okay, so if we're doing this example, magnesium and chloride. Magnesium is Mg, and it has a tendency to lose 2 electrons. Its oxidation number is +2. That's what we'll have labeled on our periodic table. And then Cl is chlorine, and it is a -1. Okay, so looking at those numbers, you want them to equal 0. Now, you can't change those numbers, but you can change how many of those numbers you have. And so the +2 is kind of what is our bigger number, obviously. Don't ignore the positive negative when I say that. And so the question really is, how many Cl's do I need to cancel out with 1 magnesium? And so you need 2, because you would have Mg +2 and then Cl -1, Cl -1, +2 -1 -1 equals 0. And so when you write this formula, you would have MgCl2. That's a C. Okay, and so it's just getting those numbers to equal. Some people will use what they call the crisscross method, and where they would take this number, not the positive, but just the number, and cross it over, and it would become that subscript. Same thing, this 1 would cross over and become this subscript. Typically, you don't write 1s. They are understood to be there, but you have 1 in this formula. You have 1 Mg and 2 Cl's. So the compound formula is MgCl2. Okay, so the same thing if I have calcium and fluorine. Calcium is +2. Oops. And fluorine is -1. So this is almost the exact same. So when I write that one, it would be CaF2. Okay, so now we come to kind of a special one. We have phosphorus and sulfur. They are both nonmetals. They were both on the right side of the periodic table. So you remember our zigzag is our separating point. 2 nonmetals. Now, if you're looking at what we have written oxidation number wise, there are both of them are negative. Remember, that's the oxidation number most often. There are exceptions. So what you would do is you would look to see, first off, which one has the higher electronegativity, which one is farther over to the right side of the periodic table. It is sulfur. And sulfur then, if you're looking at sulfur, has a -2 charge. Okay, it has 6 valence electrons to start with. That means it needs to gain 2 more. And then if you look at phosphorus, phosphorus has a -3 above it, but it is no longer going to be negative because it is bonding with or forming a compound with another element that is negative. And so you would have, one would give and one would take. Typically, I mean, they are actually sharing but to get the math right, we want to think of kind of a give and take. So here's phosphorus. Phosphorus has 5 electrons, and its outer shell would have 5 dots around it if we were still doing the dot thing. So sulfur, remember, has a higher electronegativity, so it will take all of those valence electrons. It would take all 5. If it takes 5 electrons from phosphorus, phosphorus is left with a +5. Okay, now obviously it can't take that many, just one sulfur, and so this is where we have to write the correct formula. So if you do the cross method, then this 5 will go with sulfur and this 2 will go with phosphorus. So we would have P2S5. And if you check the math, if I have 2 phosphoruses, they total have a +10. Sorry, I'm running out of room on where to write this. They have a +10 over here. And if we have 5 sulfurs, we have 5 times -2 is a -10. +10 and -10 equals 0. And so that one works out. These we won't do a lot of, but I do want to make you aware that you do work them the same way. You just have to add in that step of figuring out electronegativities. Okay, so this is a practice page. We're going to do this together in class. I'm not going to do it here just for time's sake. Again, very straightforward. There are a couple on there, like that second kind of equation that we just did. This one you have to think about a little bit more, maybe this one. So practice those if you're doing this at home already, and we will do them in class. Okay, so now next type of compound contain what they call the polyatomic ions. And these are ions that are composed of 2 or more atoms. They're covalently bonded. Excuse me, in compounds, they act like a single particle. They act like an element, but they are a group. They have their own charge and their own name, their own formula, obviously, hello, they're on the page. And above the smartboard, I do have a shorter list of these, probably what I would consider the most common ones. But when you write formulas with these, you do everything exactly the same. You use the oxidation number to figure out like how many that you need. You know, you put the formula in. So this next page we'll look at a practice or two, maybe. Okay, here we go. So writing the formula with polyatomics, same rules. So we write the symbol. So sodium is Na. Its oxidation number is +1. Phosphate is PO4, capital P, capital O, and 4 O. So 1 P, 4 O's. And its oxidation number is -3. So same thing. I need to figure out how to make those equal 0. So hopefully, you know, you can do the crossover if you think about the math. I need 3 NAs and 1 PO4. So typically you could just write it like this. You can also go ahead and put parentheses around the PO4 to designate it's a polyatomic. I kind of recommend that just so you always kind of keep them kind of separate in your head. But however you want to work it. Now our next example though, you have to put parentheses, and we'll talk about why in a second. But let's start out. So you have magnesium, Mg, it's +2. Hydroxide is OH. Its oxidation number is -1. That's from the page before. It's also up above my smartboard. I also will have you write some of these on your periodic table. Okay, so I've got +2 and -1. So to get that to equal 0, I would need an Mg and I would need 2 OHs. Now here's the big deal with the parentheses. I need 2 of both the O and the H, so I have to put parentheses around it because this is telling me 1 Mg, 2 O's, and 2 H's. If you write it like this without parentheses, MgOH2, that's 1 O and 2 H's, and that, my friends, is wrong. Okay, so always put parentheses around polyatomics if you need to put another subscript like this 2 that we put. You don't have to always use them, but it's not a bad habit to get into. Okay, so here's another practice page. Again, we'll do this in class. Look at it if you're doing this at home, and then we will talk about it. Okay, so now naming compounds. So now what do you do if you have the name and you're writing, or excuse me, you have the formula and you're writing the name? Pretty straightforward steps for the most part. And we're going to start with binary compounds. This is when you have two elements in your compound, just two. So if you have a metal and a non-metal, so remember the zigzag on your periodic table, the dividing line, if you have something from the left and something from the right, here's the naming. You write the metal name first and you just write it like normal, just whatever it is. And then the non-metal name comes second and you change the ending to IDE. This is going to sound familiar to you guys when we say some of these words, because that ending is what we use, and so you'll have heard this. So most common one of all probably for us, NaCl. Na is sodium, and then Cl is chlorine, but we change the ending to "ide" and you get sodium chloride. Okay, that's just salt. Okay, and that's all you do. On these, like in this next example, the subscripts, the little numbers that are in there, don't change a thing. They don't, you don't do anything, you don't do any information about the number, you still are just naming the elements. So Mg is magnesium, and then F is fluorine, and that becomes fluoride. All right, so there we go. So very straightforward. Like I said, we'll do a lot of practice, and some of you are it's gonna click really quick, which will be great. And some of you, if it doesn't, we'll do a lot of practice. Lulu, the cat, wants to help us. Okay. All right. So now the second type of binary compound is non-metal plus non-metal. So two elements that are on the right side of the periodic table, the right side of the zigzag. These, we do talk about the numbers in the name. We don't have to do any real math, but we do use prefixes. And we use these prefixes to tell what the number is. Most of these prefixes should be familiar to you from geometry or the shapes, like the numbers of sides. So you'll write those on your periodic table so that you have them, and then you just follow the steps. So, excuse me, shush, Lulu. Okay, so write the first element name as normal and use the correct suffix. So in our example, we've got P2S5. So the prefix for 2 is di, and P is phosphorus. So we would say diphosphorus. Sorry that this is not written very neatly. Pen doesn't work that great. So diphosphorus is the first part, and then we have S5. The ending on this one is the second element. I have to change the ending to "ide." So 5 is penta, so we would have penta, sol, and then fide, because we're changing that ending, pentasulfide. Diphosphorus pentasulfide is P2S5. Okay, then the next one, CCl4, two nonmetals. They're both on the right side of the zigzag. One carbon, and so I would have monocarbon. Oops, monocarbon. And then Cl4. 4 is tetra, and then Cl is chlorine, becomes chloride. So monocarbon tetra chloride. Oop. All right, so pretty straightforward, I think, and then you kind of just keep on going. The big thing on this is not to overuse prefixes. Like it always seems like once I teach prefixes, and everybody wants to use prefixes all the time. Only is if you have two nonmetals. Okay, so now what about the polyatomic? So now, how do we name them if they have a polyatomic in there? These are the easy ones, in my opinion. If you have a metal plus a polyatomic, so the metal is first and the polyatomic is second. Metal name is normal, polyatomic name is normal. So boom, I don't change any endings. I don't add prefixes. I just, in this case, would say sodium hydroxide. That one does have the "ide" ending already, but it's just because it's part of the name. Okay, then the next one, MgCO3. This you have to kind of train your brain to picture that, or to recognize that there is a polyatomic. So you've got the CO3 is your polyatomic, just like up here was the OH. Okay, so when you name them, you have magnesium carbonate. And every year I always have students who want to name the elements individually, and I will get a lot of magnesium carbon trioxides, or just kind of random names. That is not the correct format. You want to name that polyatomic together. So when you're looking at the symbols for a compound, the formula for the compound, first thing I would advise you to do is count the number of elements. If it's 2 elements, you name it like we did on the previous pages. If it's 3 or more, then you know there's a polyatomic, and then you can look for it. And if you don't recognize a polyatomic, then compare it to your list, and then put parentheses around it like I did, or circle it or whatever, and then name it correctly. Okay, that's the second big mistake naming wise. Too many prefixes, and then not naming the polyatomics as a group. Okay, so now the one other polyatomic naming format is if the polyatomic comes first. There's one polyatomic that will be written first, and that is ammonium. Ammonium is written first because it has a positive charge. It's the only polyatomic with a positive charge. I don't think I've even said this, but when you write a compound, the positive ion comes first. Okay, so you write the polyatomic name as normal, so in this case ammonium, and then you would write the nonmetal name and change the ending to "ide." So this NH4Cl is ammonium chloride. Okay, all right, so here's practice all types of compounds. So again, if you're watching this early, these are in your notes, so look them over. We'll do this together in class. Okay, so now chemical reactions. So now kind of putting all these things together. In a chemical reaction, typically kind of the bottom line is that you have a rearrangement of the atoms in compounds to form new compounds. When a chemical reaction has taken place, when you have a new compound, you will typically be able to observe one or more of the following. You will see a solid that separates from a liquid. We will call that a precipitate. A gas is formed. We will see that as bubbles. The colors change permanently. Sometimes they'll change but then go back to the original, fairly rapidly. If they stay a different color, that's a chemical reaction. The temperature of the substances change. Now, this is not you heating it up on the Bunsen burner or you putting it, like in ice or on the refrigerator. This is you add 2 different substances together and they make the beaker feel hot, or and that's the more common one, but there are some reactions that will make things feel colder. And then the last one, light or sound is produced. We typically won't deal with anything like this. That's more a biology chemical reaction, at least from my experience, but that is a possibility. One other one that's not on this list, so I didn't include it because it's not in your book, is that an odor is produced. And so again, kind of depends on your source, but these are kind of the main things that you see. Okay, so in reactions, you have reactions containing different pieces of information. They have chemical formulas, and they represent just the chemical composition of substances like we've already talked about. And then you have the chemical equations. And the equations represent the changes that take place in the substances during the reaction. So they are using the formulas to show you kind of what is produced, what you get. And so this is a typical, I know that page seems really busy. This is a typical reaction. I'll draw a line kind of to mark this out. And you have 2 sides to it. You have reactants over here. So these are all reactants. There's a reactant plus that reactant. Reactants are what you start with, and then they will produce the product. Let me circle that, make it look right. Okay, and so sometimes you have 1 reactant and 2 products. Sometimes you have 2 reactants and 2 products. It's all different combinations, but the arrow is always going to point to the product. It is pointed to what is being produced. Now, you also have a lot of numbers. Typically, you have coefficients, which we will talk about in a minute. Sorry, my dog is right outside the window rolling in the grass and it's being weird. Max. Okay, so then you have coefficients, which we'll talk about with balancing the equation. And then you have subscripts, which we've been dealing with when we've been writing formulas. And then this third little thing I've labeled over here is state of matter. This little G means that H2O, which is water as we know it, it is in its gas form. So over here, oxygen in the gas form, hydrogen in a gas form. Okay. So in these reactions, you use all the different numbers to make both sides equal. And you can think of the arrow as an equal sign. So let's do the practice down here. So I have this kind of labeled as take an inventory. How many reactants do you have and how many products do you have? So what you want to do is look at the individual elements. So we're going to start with carbon. So here's carbon. Here's carbon down here. I've got C6. That tells me that I have 6 carbons. Same thing with the H. I've got an H and I've got 12 H's. Then the O's. Look at the O's. They're in 2 different spots. I have 6 in this first reactant. And then over here, I just have oxygen by itself, but I have 6. And in each oxygen, there are 2. So you would multiply this 6 times 2 is 12 plus this 6, and I would get 18. I'm sorry. Okay, so what I should see if this is a correctly balanced equation is that I should see the same numbers on the other side. Okay, so let's start again with our carbon. Here's carbon. So now this time the 6 is in front, but I just have 1 carbon. So 6 times 1 is 6. Hydrogen, we'll go in the same order. Here's hydrogen next. I have 6 in front of these 2 hydrogens. 6 times 2 is 12. And then my O's, I have, again, 6 times 2, so I've got 12 O's over here. And then 6 times 1 is 6. 12 plus 6 is 18. So, good to go. And that's what that whole reaction represents. It tells you how many you start with, what it is, what state of matter it might be, and then it tells how much you end up with. So you could write out what happens in a chemical reaction in a long sentence, a long, description. This is just making it shorter. Okay, so now when you write equations, 5 main steps that we're going to worry about. First off, you got to write the correct formula, which is why we've done the rest of this chapter. One thing to note is if it is a diatomic element, remember you have the 7 diatomic elements, There's always 2 of those. And so if I said something like hydrogen reacts, you would put H2. Sorry, Max, still being weird. Okay, so anything else, you would write the formula like we've been practicing. If you are given enough information, you need to write the symbols for the state of matter. So if you know it's a solid, liquid, or gas, you would put that. By the way, sometimes the word precipitate is used, and that does mean solid. And then another, probably the most common symbol is AQ. AQ means that it is something dissolved in water, and that stands for aqueous. Most of the solutions that we deal with in life are aqueous. And so anyway, it will give you that kind of description, or I will give you that kind of description if I want you to add that information in. And then some other symbols, if you're describing it, it'll say yields or produces or forms. That's where you put your arrow. And or combines with or reacts with is a plus sign. You're putting those 2 things together. Sometimes it will say that heat is needed. Heat is typically represented by a little triangle. I in my mind always imagine that that's like supposed to represent a little flame. I don't even know, honestly. I just assume that. But anyway, and then you balance the equation. So the next thing we're going to do is practice balancing. Okay, so first things first, when you balance, you only use coefficients. Now, I'm going to do one of these with you here just to make sure everybody's kind of got the steps and all, then you can do the rest, and we'll do the others in class also. But it is a back and forth, checking the first side of where the reactants are, and then the other side of the arrow where the products are. And you just go back and forth and you put numbers, and specifically the numbers that you put are coefficients, until you have equal amounts on both sides. So if we start with that first one, you have Zn plus O2 produces ZNO. Okay, so start with your zincs. On this side of the reaction, right now, you have one zinc. On this side, right now, you have one zinc. Yay, so they're already balanced. So you leave those alone. And then you go to the next element, oxygen. Now this one, I have two O's here. And then over here, I have one. Now, the only thing that you can do to fix that is use a coefficient. And the only place that you can put coefficients are in front of the whole entire compound. I can't just randomly put a 2 behind the O or squish it in the middle of that compound and put it between the Zn and the O. That's not how it works. I can only put it here. So I would have to put a 2 here, but then I messed up my zincs because now in this, because of that 2, I now have 2 of everything behind it. I have 2 zincs and I have 2 O's. So my O's are good, but I messed up my zincs. So if I have 2 on this side, I have to come back over here and put a 2 on that side. So now I have 2 zincs and 2 zincs, back and forth, 2 O's and 2 O's. If it makes you feel better to have the every blank filled in on your equation, you can put a 1 here and it doesn't change anything, but you know that you've checked it. I personally will put the 1. Okay, so practice those other ones. We'll do them in class, like I said, back and forth, back and forth. I recommend you use a pencil, especially as we first get started, but it is just a kind of an inventory. Okay, so now writing equations, again, we will do this example in class, but it is basically writing formulas, using the symbols, and then balancing. So see what you can do with this, and then we'll go over it in class. Oh, here's another practice page, and same thing, keep on with that. Okay, and then last thing, the types of reactions. What is actually happening in the reaction, like how many reactants, how many products, kind of what goes on, can also be described. And there are five things that I want you to know, or 5 types of reactions that I want you to know. Here are the first 3, and then we'll finish up. First off, composition. Composition is when you have 2 or more substances that react to form one substance. So here I've got my S plus my O2, and they make SO2. So it's basically things going together. Decomposition is the opposite. You have one substance that breaks down into 2 or more smaller, simpler substances. Okay, so 1 CaCO3 breaking down into 2 CaO and CO2. And so you obviously won't have these exact same letters or elements or whatever, but look and kind of see what's happening. Do I have one thing do I have 2 things forming one thing, or one thing breaking down into 2? And just kind of see if you can tell. And then single replacement. Single replacement is when you have a single element and it replaces an element that is in a compound. So what you have to do is look on either side of the reaction. I've got a single element here, and then over here I've got a different single element, which basically means that zinc took the place of that hydrogen. They just traded places. So I've got 2 different single elements on either side of the equation. Again, pretty common. Just kind of follow the pattern as you're looking through to determine the type of reaction. Okay, then last 2, double replacement. You've got 4 compounds, 2 reactants and 2 products, and the metals, as typically how I look at it, the metals trade places. So I started with AgNO3, and then over here I have AgCl. That's because the Ag and the K traded places. So they flipped. And so I end up with the K going with the NO3, the Ag with the Cl. So 4 total compounds, but just with a rearrangement or with a switch in the products. Okay, and then last one, you guys know this one already, or you've heard these words. Exothermic and endothermic are reactions where you know what's happening with the energy. Energy is represented as heat. And so in exothermic reactions, energy is given off as one of the products. So it is over on the right side of the reaction. And then in endothermic, the reaction has to absorb heat energy. And so heat is over here on the reactant side. All right, so it's just kind of following the pattern on these. Okay, that's a long video, a lot to say. It's going to take us a while. We'll start this before spring break and come back to it after spring break. So good luck. Ask me questions in class as always, and I'll see you.